This is the fifth video in a series devoted to abstract algebra. And for the previous few videos, we've been looking at examples of groups. And today we're going to also look at some examples of groups. And this is maybe one of the most important classes of examples that we'll look at today, the so-called permutation groups. And starting in the next video, we'll be proving some general results about groups. And so by that point, we'll have tons of examples to work with and build intuition. Okay, so let's jump into our first definition. So given a set X, a permutation of X is a bijection from X to itself. And then you can wrap up all of these bijections into a set called Sx. And that's going to be all sigma from X to X such that sigma is a bijection. So this is just the set of all bijections from X to itself. So let's look at some examples. If X is the set containing 1, 2, 3, 4, sigma could have the following action. So I've put it all together in this single diagram. So sigma sends 1 to 2. So we want to read this as sigma evaluated at 1 equals 2. And then sigma sends 2 to 3. So in turn, we read that as sigma evaluated at 2 equals 3. And then sigma sends 3 to 1. And then finally, sigma fixes 4, so it sends 4 to itself. So this is definitely a one-to-one and on-to function. In other words, it's a bijection. So this is an example. And then for another example, let's take X to be all real numbers. And then we'll take the function that takes X to X cubed. So this is also clearly a bijection, which makes it a permutation of the real numbers. Next, let's take X to be the integers, and then we'll have our bijection be the shift bijection. So it takes n to n plus 1. Okay, so now that we've seen some examples, let's maybe prove a very important result about Sx, and that is it's indeed a group. And so we'll show that for all non-empty sets X, Sx is a group. So the first thing that we need to do here is prove that we indeed have closure. So generally we take closure kind of as a given, but I think it's maybe a good practice to prove closure in this case because it means we have to dive into the definitions of injectivity and surjectivity. Okay, so let's suppose that sigma and mu are in Sx. Well, what does that really mean? That means that sigma and mu are functions from X to X, which are bijections. So we've written that down now. So we have sigma and mu are both bijections. So in order to prove closure, we need sigma composed with mu to be a bijection. And I guess I kind of got ahead of myself. What's the operation for this group? Well, the operation is composition of functions. So now let's do that. So we'll maybe prove that as a little bit of a subclaim. So we'll write the claim here, and that is that sigma composed with mu is in Sx. That means it's a bijection. Okay, so let's first show that it's an injection. So here, we need to show that it's injective. So let's suppose that sigma composed with mu composed with A is equal to sigma composed with mu composed with B, or evaluated at A and B, I should say. And here A and B are arbitrary elements of our set X. But let's note that that means that sigma of mu of A equals sigma of mu of B. That's just the definition of composition of functions. But now we can just unravel this one bit at a time using our injectivity. So since sigma is injective, we know that mu A equals mu B. But then since mu is injective, we know this implies that A equals B. So let's look at what we've done. We started with sigma mu evaluated at A equals sigma mu evaluated at B, and we ended with A equals B. So that's exactly what we need for sigma composed with mu to be injective. Great. So that's the first part of showing that it is bijective. And if it's bijective, then it's in this set up here, Sx. Okay. So the next bit we need to do is prove that it is indeed also surjective. Okay, so how might we do that? Well, let's maybe take some arbitrary b in x, and we want to find a preimage for that b that gets mapped onto by sigma composed with mu. So now the first thing that we want to do is maybe find something that I'll call c in x such that sigma of c equals b. So that's possible because sigma is surjective by our assumption. And then also we'll find an a in x such that mu of a equals c. And so it's important to do it in that order. And again, that's possible because mu is a bijection and thus it is surjective. Okay, so now let's put this all together. So let's notice that sigma composed with mu evaluated at A is indeed sigma of mu of A by the definition of composition, but that's going to be sigma of C by the way that we chose A, but then sigma of C is equal to B. Okay, so let's see what we've done. We took an arbitrary b in the codomain, and we found some element of the domain where sigma composed with mu evaluated at that element lands on the place that we want it to land on. So that's exactly what we need for this to be surjective, but since it's surjective and injective, it's bijective, but that's what it means to be inside of Sx, so that means we indeed do have closure. So we could maybe go over here and put a check mark next to closure, and then move on to the other parts of a group. So we just finished proving closure for our set Sx and composition. Now we'd like to prove that we indeed have an identity. And there's an obvious identity function. We'll call this maybe iota. So we're going to take this from x to x, and it's going to be defined as iota evaluated at little x equals x. Great. And now we can just maybe very, very easily notice that if we take sigma composed with iota and we evaluate it at any x, we'll get sigma evaluated at x. But since this is occurring for any small x, that means that sigma composed with iota is equal to sigma. But that's maybe half of what we need for this to be an identity type element. The other half would be to show that iota composed with sigma is also equal to sigma, but that follows almost immediately. And then finally, one tiny last thing that we would have to prove. I say that it's tiny because it's very, very obvious, if you will. And that is that this is indeed also a bijection, which means it's inside of Sx. But I'll let you guys check that that's a bijection. There's not really much to that. Okay, so putting that all together, we definitely have an identity element inside of Sx. The next thing that we might want to prove is that we have inverses. So let's maybe do that. So let's go down here and we'll prove that we can find an inverse for everything inside of Sx. So let's take sigma from x to x, and we'll define something which we'll call mu from x to x by the following rule. So mu of b is equal to a if and only if sigma of a is equal to b. And now whenever you're making this sort of definition, you need to check that it's well defined. Because indeed, if our function is not surjective or not injective, then this may not make any sense. But the fact that it's bijective means that we can indeed do this. So like I said, we need to show that this thing is well defined. So what does that mean? Well, let's suppose that under this setup, we have mu of b is equal to a1 and mu of b is equal to a2. So a priori, we don't know that mu is a function. It could simply be a relation. Okay, but notice that by our definition of mu, this means that sigma of a1 equals b, which is also equal to sigma of a2. But that means that a1 is equal to a2. But it may not seem like we did anything here, but looking at that in terms of this right here, we see that mu is a well-defined function in that there's only one place that we can send any element of the domain. We tried to send it to two places and we showed that those two places were the same. Okay, so now let's maybe move on and prove that this function is indeed also injective. Okay, so now how might we do that? Well, let's take mu of a equal to mu of b, and let's maybe set that equal to something which we'll call c. But under our definition right here, that tells us that sigma of c is equal to a and sigma of c is equal to b. But now since sigma is a well-defined function, that tells us that a is equal to b, which is the injectivity condition for mu. Okay, so we've got our function is well-defined, it's injective. Now I'll leave it to you to prove that it's surjective. That would be a nice homework. And what's left to show is that we actually compose to the identity. So let's do that. Okay, so now we need to show that sigma and mu compose to the identity in both orders, if you will. So let's do that by considering the following object. So sigma composed with mu evaluated at little x, where little x is something arbitrary inside of big X. Okay, so let's introduce a little bit more notation to take advantage of this line right here. So let's maybe set mu of x equal to y. But notice that's equivalent to saying that sigma of y is equal to x. Okay, great. But now we can decompose this thing into sigma of mu of x. But by our notation over there, that's equal to sigma of y, but that's equal to x. So we see that sigma composed with mu is equal to, well, just whatever we started with. But that means that we have sigma composed with mu is indeed equal to the identity function. Now we also need to check that mu composed with sigma is also equal to the identity function, but like we did with the last bit, I'll let you guys check this on your own. These are indeed like some really famous exercises that you might see in a discrete math or an intro to proofs class. That's why I'm kind of going through them quickly. They're of course in that class not done under the setup of a group, they're just done under the setup of studying functions. Okay, so anyway, we have shown that we have inverses, and the last thing to do is show that we indeed have associativity. We've got one last thing to prove so that Sx is a group, and that is we have associativity with composition. So let's see how we might do that. So let's suppose that we have sigma mu, and then maybe my last one I'll call nu, and these are all inside of Sx. And then let's also suppose that we've got a lowercase x inside of capital X, and this is an arbitrary element of capital X. And we need to work through this test element, because if we work through this test element and we have associativity, since this was chosen arbitrarily, then we have associativity like as functions. Okay, so now let's consider the following object. So it'll be sigma composed with mu composed with nu evaluated at x. So that's going to end up being sigma of mu composed with nu evaluated at x, just based off of how our parentheses are with this setup. Okay, so now let's work on this inside, and this inside is going to simplify to mu of nu of x. Great. So we end up with sigma of mu of nu of x. Okay. And now we're ready to decompose this. So this is going to be equal to sigma composed with mu evaluated at nu of x. Just like using definitions of composition and the like. But now we can take that one more step and see that we have sigma composed with mu composed with nu evaluated at x. But like I said, since x was chosen arbitrarily, we have this function right here that I'm underlining in blue is equal to this function down here that I'm also underlining in blue. But the equality of those two functions is exactly what we need for associativity. Which means we've proven the 4 main axioms for Sx to be a group, so that's great. We've got a new example of a group. Now, let's look at some special examples of Sx where x is like a nice set. So probably the most widely studied permutation group is the permutation group where you take x to be the set containing 1, 2, 3, 4 up to n. And then in that case, you call this the permutation group on n objects. And you denote it by s underscore n. And so you read that Sn. But like I said before, that's exactly the group Sx, where x is this set that we described earlier. Now I'd like to do a quick observation without a proof. The proof of this is like fairly standard from a counting argument, which I don't mean to throw this back to a previous course, but you likely saw in an Intro to Proofs class. And that is the number of elements of Sn is equal to n factorial. Recall, that's just counting the number of permutations of an n element set, but the number of permutations of an n element set is n factorial. Okay, so let's do a couple of examples. So let's have 2 elements of S4. So these are permutations on the set 1, 2, 3, 4. I've noted them sigma and mu. And sigma has the following action. It takes 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Whereas mu sends 1 to 3, 2 to 4, 3 to 2, and 4 to 1. And now we'd like to get a handle on a couple of things. Maybe what the inverses are, as well as what compositions do. Okay, so let's maybe first notice what the inverses are. Let's just do sigma inverse, because mu inverse will be essentially the same thing. So since my notation is just to put all of the elements of 1, 2, 3, 4 at the top row in order, that's what I'll do. And now I need to see what happens to 1 under sigma inverse, 2 under sigma inverse, and so on and so forth. But the inverse function will simply reverse the arrow that we have right here. So that means 1 will get sent to 4, because in sigma, 4 gets sent to 1, and if we reverse the arrow, like I said, 1 gets sent to 4. So that's what we have here. That's our first description of what sigma inverse does. And then let's notice that 2 gets sent to 1, 3 gets sent to 2, and 4 gets sent to 3. Okay, so that's good. That's a nice description of sigma inverse. We'll have a more compact description for these types of permutations later, but not quite yet. Okay, so now let's next calculate sigma composed with mu. And we'll start again with 1, 2, 3, 4 here. And then let's start our arrows just to get ahead of the game. And so let's recall that we operate with mu first. And we operate with mu first because this is composition of functions. So let's maybe do the calculation for some of these out kind of long over here. So the first thing that we need is sigma of mu of 1. So that would be sigma composed with mu evaluated at 1. Okay, but mu of 1 is equal to 3 based off of this description right here. So this is sigma of 3. But then sigma of 3 is 4 based off of the description up here. So in the end, sigma of mu of 1 is 4. So that means we would put 4 down here as the image of 1. Okay, so let's do another. Let's do sigma of mu of 2 and see what we get. So mu of 2 is 4, so that's going to be sigma of 4, and then sigma of 4 is 1, so that brings us back to 1. Okay, so that means in the end, sigma of mu of 2 is 1. We end up with something like that. Okay, now let's see what happens to 3. So let's maybe extend this down here so that we've got enough room. So like I said, we need to look at sigma of mu of the number 3. So that's going to be sigma of, well, mu of 3 is 2. Okay. And then sigma of 2 is, so this is interesting. Sigma composed with mu fixes the number 3. It sends 3 to itself. But now we actually don't need to make this last calculation because we can use the fact that we have a bijective function. And the only thing that we're missing here is the number 2. So that means 4 must be sent to 2. I'll let you guys check that if you need to. Okay, so now let's do a midpoint exercise, or I'll give you a midpoint exercise, and that is to compose mu of sigma. And what you'll see is that it is indeed non-commutative. So that shouldn't be a surprise. You should be familiar with the fact that composition of functions is non-commutative. Okay, so now that we've done some starter calculations, next up I want to introduce a powerful notational tool for working with these permutations. Now we're going to look at a really powerful tool for simplifying calculations within Sn. That's called cycle notation. So let's say we've got sigma and mu inside of S5, and they're defined as follows. So briefly, sigma takes 1 to 3, 2 to 4, 3 to 2, 4 to 5, I should say, and 5 back to 1. So that means that sigma evaluated at 1 is 3, and so on and so forth, like we saw on the previous board. And now we'd like to put all of this information into a more compact form. Okay, so let's get started. I'm just going to talk our way through this example, and after we've seen this with a few examples, I think it'll be fairly clear how to write this down in general. Okay, so sigma will be equal to the following cycle notated permutation. So I open a parentheses like this, and what I'll have here is something that looks like a row vector, but it's not a row vector, it is a cycle notated permutation. Okay, so I'm going to start with the number 1. And then I'll look up here and I'll see where 1 is mapped under our permutation. And notice that 1 is mapped to 3. So that tells me to put a 3 here. And then looking back on it, when I read my cycle notated permutation, I'll know that sigma takes 1 and sends it to 3. Okay, and now I keep going. Now I take 3 and I look, oh, 3 gets mapped to 2, so that tells me to put a 2 here. So again, if we look back on it, we see that sigma of 3 is equal to 2, just based off of this notation. The idea is that sigma of anything in this row is the next element of the row. Okay, so let's keep going. So sigma of 2 is 4, so that means we put a 4 here. Sigma of 4 is 5, so that means we put a 5 here. And then sigma of 5 is 1, but 1 is at the beginning. That tells us to close this off. Okay, so that's the cycle notated version of sigma. Now I'd like to notice that this could also be put in a circle as follows. So we have 1, 3, 2, 4, 5. And then this arrow is an application of sigma. So this is maybe the nice graphical way of looking at it, is we have this loop occurring within the set containing 1, 2, 3, 4, 5 under this action of sigma. And this like cycle notated version is just like a maybe smaller way of writing this loop. So now let's see what's happening with mu. So mu will equal, well, we'll start with 1 again, and let's notice that 1 gets sent to 4, so I put a 4 here. Then 4 gets sent to 1, but that's back to where we started, so we close this off. Okay, so we've got 4 sent to 1. But then we start with the next smallest number that we haven't seen. In this case, it is 2. And then we go through the whole game again. So 2 gets sent to 5, 5 gets sent to 3, and then 3 gets sent back to 2, so that closes our loop. So now notice we've got two cycles here and they're disjoint. So we would call these disjoint because they don't share any of the same numbers. Further, we would call this a 2 cycle because it contains 2 elements. And this is a 3 cycle, it contains 3 numbers, whereas this is a 5 cycle. So in particular, an M cycle is a cycle containing M numbers. Now, if we were to draw a picture of this, it would contain 2 disjoint loops. So we've got this loop between 1 and 4, and this loop between 2, 5, and 3. So we have something like that going on. So now that we've kind of motivated this construction of our cycle notation, let's do some calculations using cycle notation. So now we're going to work with our permutations mu and sigma and see what happens when we compose them and how we can easily compose them using this cycle notation calculation. Okay, so let's first look at sigma composed with mu. So I'll put the cycles just next to each other and then we'll work through how this goes. Okay, so there I have all of my cycles next to each other. And now, remember, we want to build this into something that's a cycle on its own. You might say, well, we're done here, but there can be quite a bit of simplification. That's because we do not have disjoint cycles anymore. We can always do a calculation until we get disjoint cycles. Okay, so let's start with the number 1. We always really want to start with the number 1. And now let's recall that these are functions. So we want to think about sending the number 1 through these permutations. So as 1 passes between 2, 3, and 5, or between that cycle, it doesn't change. And that's because 2, 3, 5 is not acting on 1. But now as 1 passes through this 2 cycle, 1, 4, it does change. It gets sent to 4. And then finally, as 4 gets sent past this one, it turns into 5. So that means in the end, like in the conglomerate, 1 gets sent to 5. Okay, so now let's work out another one. So let's go to 5 at this point, because that's the one right after 1, or that's where 1 was sent. Okay, so let's start here, 5. So under this first 3 cycle, 5 is sent to the number 3, and then it's fixed by this 2 cycle, and then by this 5 cycle, 3 is sent to 2. So in the end, we'll see that 5 is sent to the number 2, so that tells us to put a 2 right here. Now let's see what happens to the number 2. Okay, so we'll put a 2 here. In the first 3 cycle, 2 is mapped to 5, and then it gets fixed by this 2 cycle 1, 4, and then in this case, 5 gets sent back to 1. So in the end, 2 is sent to the number 1, but that means we need to close this off. Then we'll pick up with the next smallest number. So in that case, this is 3. So let's see what happens here. So under this first map, 3 gets sent to 2, 2 gets sent to itself because we've got 1, 4. And then here, 2 gets sent to 4. So in the end, 3 is sent to 4. Great. But now we need to look at where 4 could be mapped. And in fact, we know immediately that 4 has to be mapped to 3, given the fact that we have injectivity. So that means we can close this off. So now in the end, if we wanted to put this all together, we would see that sigma composed with mu is this product of our 3 cycle and our 2 cycle. So 1, 5, 2, and then 3, 4. Okay, so now for practice, let's calculate mu sigma. So mu composed with sigma, so that means I need to write 1, 4, 2, 5, 3, and then 1, 3, 2, 4, 5. Okay, so we want to start with 1. And I'm not going to muddy up the board with these calculations anymore. I think we can just do it by eye. So let's see. Under this first cycle, 1 is sent to 3. Under the second one, 3 is sent to 2. And under this one, 2 is sent to itself. So in the conglomerate, we have 1 is sent to 2. So we would put a 2 there. Now let's move on to 2. So under this first cycle, 2 is sent to 4. 4 gets fixed in this case, and then 4 is sent back to 1. So that means we've got a 2 cycle here of 1, 2. Okay, now moving on to the next smallest number, that will be 3. So under this first map, 3 gets sent to 2, and then we see 2 gets sent to 5, 5 is sent to itself. So in the end, 3 is sent to 5. Okay, so now let's see. 5 gets sent to 1, and then 1 gets sent to 4 over here. So that closes everything up because we've exhausted all of our numbers. So in the end, we've got that 2 cycle times the 3 cycle, 1, 2 times 3, 4, 3, 5, 4. Okay, let's do one more maybe. Let's do mu squared. Well, actually, let's do mu squared and also sigma inverse. There's a nice trick for calculating inverses. So mu squared will be to do 1, 4, 2, 5, 3, and then 1, 4, 2, 5, 3. So now let's see what happens to 1. So under this map, 1 is sent to itself, 1 is sent to 4, 4 is sent to itself, 4 is sent back to 1. So in the end, 1 is sent to itself. So we would write that as just maybe 1 by itself like this. And now let's move on to 2. So here, 2 is sent to 5, and then 5 is sent to 3. So in the end, 2 is sent to 3. And then let's see what happens to 3. So 3 is sent to 2 here, and then 2 is sent back to 5, and then it's sent to itself here. So that means 3 is sent to 5. And then since there's only one more number left over, and that's 4, it must be sent to itself. So here we have this is equal to 2, 3, 5. But now let's notice that we could have calculated this much easier, and that's by the fact that since these are disjoint, they're commutative. So that's maybe something that's obvious. We'll maybe sketch a proof of it later, but we won't right now. So that means we could in fact write this as 1, 4, 1, 4, and then 2, 5, 3, 2, 5, 3. But that's exactly equal to 1, 4 squared, and then 2, 5, 3 squared. And then a quick way to calculate squares of cycles is just to count through them 2 numbers at a time instead of 1 number at a time. So here we know that with 1, 4, 1 is sent to 4, but with 1, 4 squared, 1 goes back to 1 because we count twice. And similarly, 4 gets sent to 4 because we count through twice. And then here, 2 gets sent to 3 because we count through twice. And then 3 gets sent to 5 because we count through twice. And then likewise, 5 gets sent to 2 because we count through twice. So that's a quick way of doing that. Okay, so before we move on to some general results involving cycles, what I'd like to do is look at the inverse of sigma. There's a nice trick for calculating inverse. So finding inverses in cycle notation is quite easy. All you have to do is use the following rule, and that is to find inverses, read backwards. So what do I mean by that? Well, in general, we're reading from left to right. We know that this means 1 goes to 3, 3 goes to 2, so on and so forth. So reading backwards would be reading right to left, just keeping in mind that these are loops. Or if we had that circle drawn, that would be reading counterclockwise versus clockwise, depending on how you've oriented it. So that means we can easily calculate sigma inverse. So let's see, we'll start with 1, but reading backwards, that goes to 5. 5 goes to 4, 4 goes to 2, 2 goes to 3, 3 goes back to 1, so that closes it off. And then if you want to really be sure of this, maybe for the first time or two, you might want to check that sigma composed with sigma inverse is the same thing as sigma inverse composed with sigma, which is the identity. And now is a great time to write down the notation for the identity in interval notation. And you know, there are several notations that you see throughout the literature, but the one that we'll use is just a 1 cycle with the number 1 in it. We'll read that to be just the identity permutation. Okay, so now let's do the same thing for mu. So mu inverse. So again, we'd like to read backwards. So we'll start with 1, but if we read backwards here, 1 is still sent to 4. That's because it's a 2 cycle, so reading forwards and backwards is the same. 4 also gets sent to 1 for the same sort of reason. Now let's start with 2. If we read backwards, 2 gets sent to 3, which gets sent back to 5, which gets sent back to 2. So that means we have this. Okay, so that's good. Now let's look at some general results. Okay, so here are a couple of facts which are pretty evident, but if you don't see the proof of these immediately, it might be nice to seek them out. There are several open source algebra books or notes online where you can find proofs of the following results. So the first one says that every sigma in Sn can be written as the product of disjoint cycles. So in fact, the way that we started by writing things as products of disjoint cycles builds the proof, if you just generalize that to a general permutation. And then the next one is that disjoint cycles commute. And that's really because disjoint cycles have disjoint domains. So you're not even plugging the same sort of numbers into them. Okay. And then finally, the order of an M cycle, so that's a cycle of length M, is M. So that's nice. So maybe the canonical M cycle would be 1, 2, 3 up to M, and the order of that is M. Let's recall that the order is the smallest natural number, where if you raise a group element to that natural number, you get back to the identity. Okay, so let's prove the following lemma about the order of an element of a group, which will be used to prove a nice result regarding orders of elements in the permutation group. So let's suppose that G is a group and the order of G is n. Then G to the m is the identity if and only if n divides m. So let's maybe do the reverse direction first. Notice this is an if and only if statement, so there are two things to prove. So let's suppose that n divides m, but that means that m is equal to n times k for some integer k, but here we can take this to be a natural number. I should have maybe restricted these to natural numbers, but let's not worry about that. Okay, so now let's notice that g to the m is equal to g to the nk, which is equal to g to the n, all raised to the k. But if the order of g is equal to n, that means g to the n is the identity, but the identity E combined with itself any number of times is always the identity. So there we have it. So now let's go in the forward direction. So let's suppose that g to the m equals e, and next we'll use the division algorithm, which we recalled in a previous video, with m and n. And so this will be to write the following. So we'll have m is equal to n times q plus r, where r is between 0 and n. So like I said, that's the division algorithm. Now let's look at the identity, which is equal to g to the m by our assumption, which is equal to the g to the n q plus r, which is equal to g to the n to the q times g to the r by exponent rules. But we know g to the n is the identity, given the fact that it's the order of the element g. So that means this term just turns into the identity. And so we're left with g to the r. So let's see what we have. We have g to the r is equal to the identity. But that's a problem in all cases except when r is equal to 0. Because if r is not equal to 0, that's a contradiction of the order of g is equal to n. Because n is supposed to be the smallest natural number that makes this happen, but r is strictly less than n. But since r not equal to 0 gives us a contradiction, that tells us that r must indeed be equal to 0. But now if we rewrite this line with r equals 0, we have m equals n times q, which is exactly the condition for n to divide m as needed for this other direction. Okay, so now let's apply this to cycles. So now we'll like to apply that previous result to the following lemma, which involves elements of Sn. So let's suppose that sigma 1, sigma 2 up to sigma k are disjoint cycles of length A1, A2 up to AK. And then let's also set sigma equal to the product of those disjoint cycles. So we've got sigma 1 times sigma 2 all the way up times sigma k, where of course when I say times, I really mean composition. Then the order of sigma is equal to the LCM of the length of the cycles. So the LCM of A1, A2 up to AK. Okay, so let's maybe see how this might go. We'll first start by introducing some notation. So let's set m equal to the order of sigma, and we'll set L equal to the LCM of A1 up to AK. And under this introduction of notation, our goal, in other words, what we want to show, is that m is equal to L. So let's first notice that since L is the LCM of those, it's in fact a common multiple of all of them, which means it's a multiple of A1, it's a multiple of A2, and so on and so forth. So that means we can write, let's see, L equals AJ times QJ for j between 1 and k. In other words, L is a multiple of all of those numbers. So now let's look at sigma to the L, which is the same thing as sigma 1 to the L times sigma 2 to the L, all the way up to sigma k to the L, where I use an important fact that since these are disjoint, they commute. So remember, that was this second fact over here. Otherwise, we could not do this. Okay, but now each of those can be written as sigma 1 to the A1 raised to the Q1, sigma 2 to the A2 raised to the Q2, all the way up to sigma k to the AK raised to the QK, like that. But now this other fact down here about the order of an M cycle essentially takes us home. So since sigma 1 is an A1 cycle, if we raise it to the A1, we compose it with itself A1 times, we get the identity. So this is the identity raised to the Q1 power, the identity raised to the Q2 power, all the way up. It's just a combination of the identity a bunch of times, which means here we get the identity. But now we can apply our previous lemma. So if m is the order of sigma and sigma to the L is equal to the identity, that tells us that m divides L. So now let's move on to the next part of this proof. So also we know that the identity is equal to sigma to the m, that's the order, but that's equal to sigma 1 to the m all the way up to sigma k to the m, like that. But since these are disjoint cycles, that means that all of these sigma 1 to the m, sigma 2 to the m, and so on and so forth are also disjoint cycles. So since they're disjoint cycles, they cannot be inverses of each other, which means that each of these individually has to be the identity. That's the only way that you'll get back to the identity. So all of those words I said mean that sigma 1 to the m is the same thing as sigma 2 to the m, all the way up is the same thing as sigma k to the m, which is the identity. That tells us that A1 must divide m. That's because A1 is the order of sigma 1. And it means that A2 also has to divide m. That's because A2 is the order of sigma 2. So on and so forth, we know that AK also has to divide m. But if all of those numbers divide m, that means m is a common multiple of all of those numbers. But by the definition of the least common multiple, that means that the least common multiple has to divide that number as well. So let's see what we have. We have m divides L, and we have L divides m. but implicitly we've assumed that L and M are both natural numbers. So putting this together, we see that M is equal to L, which is where we needed to finish this off. Okay, so now let's look at some applications of this theorem before we finish the video. So now to apply that theorem, we'll look at the following two examples. The first is to find an element of order 12 in S7. So when you're first learning about these types of things, it's easy to make the mistake that the largest possible order in Sn is n, but that's definitely not the case. Definitely the order of the largest cycle in Sn is n, but because of the power of multiplication, you can get an element that has a higher order. And that's exhibited by this example. So let's consider the following. 1, 2, 3, 4, and then 5, 6, 7. So that's definitely in S7. And by our facts over here, we know the order of this is equal to 4 because it's a 4 cycle. The order of this is equal to 3 because it's a 3 cycle. And then finally, the LCM of 3 and 4 is equal to 12. That's because they're relatively prime, so the LCM is simply the product. So there we have it. And I think, in fact, it's fairly simple to prove that this is the largest possible order of an element from S7. Okay, so now let's look at possible orders of elements in S5. Okay, so there's definitely an element of order 1, and that is the identity element. And let's notice that that is connected, and let's notice that's connected to everything being sent to itself. So we've got 5 1 cycles. 1 goes to 1, 2 goes to 2, 3 goes to 3, so on and so forth. But we can exhibit that as a so-called partition of the number 5. So notice that 5 is equal to 1 plus 1 plus 1 plus 1 plus 1. And we want to think about this as the cycle decomposition of this element. We have a 1 cycle, a 1 cycle, a 1 cycle, a 1 cycle, and a 1 cycle. Okay, so we could also have an element of order 2. And for example, this could be any 2 cycle. So maybe the 2 cycle 1, 2 would be a canonical example. And that's associated to having a 2 cycle and then 3 1 cycles. So that's like looking at the partition 2 plus 1 plus 1 plus 1. But there's another family of elements of order 2 as well, and those are disjoint 2 cycles. So, or we could have the 2 cycle 1, 2 with 3, 4. So since those are disjoint, the order of the product is the LCM of 2 and 2, which is equal to 2. But now that's associated to a 2 cycle, a 2 cycle, and a 1 cycle where 5 is sent to 5, and thus the partition 2 plus 2 plus 1. So we're not going to go so in depth into these partitions maybe at the moment. It's possible that we might later, but there's this nice connection between cycle decompositions and so-called partitions of integers, which are just these nice little addition problems. Okay, so now let's look at elements of order 3. There's one type of elements of order 3, and those are any 3 cycles. So there's an example of a 3 cycle, 1, 2, 3. And notice that's exhibited by the integer partition 3 plus 1 plus 1. Next, we can have an element of order 4, which is a 4 cycle. An example of that would be 1, 2, 3, 4. And that's exhibited by the partition 4 plus 1. And then 5, we could have a 5 cycle, 1 plus 2, 1, 2, 3, 4, 5. And that's exhibited by the partition, which is just 5 equals 5. And then finally, we could have an element of order 6, which again, people just learning these things may think is impossible because it's larger than 5, but based off of this example, we see it's not impossible. And that's because we could have a 3 cycle and a 2 cycle, which are disjoint, a disjoint 3 and 2 cycle. And this would be exhibited by 5 equals 3 plus 2. So notice that the order of this is 3, the order of this is 2, the order of the product is the LCM of 3 and 2, which is 6. So there, those are the possible orders of elements in S5. And we know that this is all of the possible orders because we've exhibited all possible partitions of the number 5. And these partitions are associated with elements of different types of orders. Okay, so now I'm going to leave you with a couple of warm-ups. Here are 3 warm-up exercises based on what we saw today. So the first is to write the following as a product of disjoint cycles and then find the order. So be careful, you can't really find the order very easily without first writing it as a product of disjoint cycles. So that's definitely the second thing to do. So here we've got an element of S8. So 1, 3, 5, 8, and then 3, 7, 8, and then 1, 2, 5. Then here we've got an element of S6. So 1, 2, 6, 4 inverse, and then 3, 6, 4 squared. So this gives you practice finding inverses and squares and stuff. Next, let's find all possible orders of elements of S7, and then determine the largest possible order of an element of S10, and then give an example of an element that achieves that order. And that's a good place to stop.